This research introduces a novel speedup of Jelinek and Lafferty's algorithm for computing prefix probabilities under a probabilistic context-free grammar. The proposed algorithm operates in O, n2, n3 plus n3, n2 time, making it the fastest in the literature for dense grammars in Chomsky normal form. It begins by defining key terms and concepts related to PCFGs, including the inside probability and prefix probability. The authors then derive the proposed algorithm from the Jelinek and Lafferty algorithm, providing a full derivation and proof of correctness. Additionally, they discuss how their improved algorithm can be extended to work for Sumerian-weighted CFGs. The paper also presents the CYK and Jelinek-Lafferty algorithms for computing prefix probabilities, highlighting their time complexities. The speedup introduced in this research enables more efficient computations, making it a significant contribution to the field of probabilistic context-free grammars and their applications in natural language processing. The research paper discusses an improvement to the Jelinek-Lafferty algorithm for computing prefix probabilities in probabilistic context-free grammars, PCFGs. The authors adapt the algorithm to use additional memoization, reducing the time complexity from O, n3, n3 plus, n4, to O, n2, n3 plus n3, n2. This improvement addresses the main limitation of the original formulation, making it more efficient for large grammar sizes. The paper also explores generalization to Sumerian-weighted CFGs, showing that the algorithm can work with locally normalized Sumerian weights. Additionally, the authors discuss the limitations of the algorithm, including its cubic time complexity, and highlight its usefulness for denser grammars. The paper concludes by acknowledging the contributions of other researchers in the field and referencing relevant works. The authors extend algorithm 3 to semirings, providing necessary background definitions and notation. A monoid is defined as a 3-tuple A, hollow bullet, 1, where A is a non-empty set, hollow bullet is an associative binary operation, and 1 is a left and right identity element. A sumerian is defined as a 5-tuple W equals A, circled plus, circled times, 0, 1, where A, circled plus, 0 is a commutative monoid, A, circled times, 1 is a monoid, and multiplication is distributive over addition. A sumerian is complete if it is possible to extend the addition operator circled plus to infinite sums, maintaining associativity, commutativity, and distributivity. The authors then define the unary operation of the Kleene star, denoted by a superscript asterisk operator, as the infinite sum over powers of its operand. They show how complete semirings can be lifted to square matrices, defining Sumerian matrix addition and multiplication. The set of square matrices of dimension d over a sumerian, with addition and multiplication as defined, is itself a sumerian. The authors consider a Sumerian-weighted context-free grammar, CFG, G equals n, sigma, s, r, p, w, where p is a locally normalized weighting function mapping rules to elements of a commutative Sumerian W. They define the matrix P as the square matrix of dimension n, where the entry pij corresponds to P, Xi right pointing arrow xj. The probability of getting xj from Xi at the leftmost non-terminal after exactly k derivation steps is calculated as pk, ij. Algorithm 5 presents a faster prefix probability algorithm over semirings, which precomputes p** operator using algorithm 4 and assigns Xi, xj, Xi, based on pij. The prefix probabilities are initialized, and beta is computed using algorithm 1. Subsequently, gamma and delta are calculated using equations, 16e, and 16f. The base case computation and the recursive computation of pi are also described. Proposition 4 discusses the complexity of the Sumerian-weighted version of the algorithm, highlighting its efficiency.